Hello guys, welcome to the lecture series on thermodynamics. So today we are going to discuss chapter 5, which is quasi-static process. And what is a quasi-static process? Try to understand it through an example. Also, how a quasi-static process, why we are studying this, and how does it play an important role in thermodynamics, in basic thermodynamics. So if you are new to the lecture series, if you are new to the channel, please hit like and subscribe to the channel if you like it at the end, and also share it among your colleagues. So now let's get started with the today's lecture. So we have in front of us a quasi-static process, and I have a sample, a simple picture here, and this is a sample of a piston cylinder arrangement. And let's try to see what this is exactly. So first, this is our system boundary. So I'm not saying this is a cylinder, but I'm saying this is a system boundary. Actually, this is a cylinder body because I'm taking an example of a piston and a cylinder arrangement to explain you what a quasi-static process is. So this is a system boundary and you have a cylinder body over here. Right, this is a piston. So this is our piston. This W is a weight. This is a weight. This is a weight which is on top of the piston. These are the stops. So these both are stoppers or stops, whatever you want to call them. And these stops will not allow the piston to move ahead. So this is where the system boundary ends. Now, in a simple cylinder and piston arrangement, what is basically happening is we have a mixture here. It could be gas, fluid, whatever. So we have a mixture here. Let's say this is gas and these are gas molecules. So these are gas molecules. It will be random. I actually shouldn't make it very laminar. Yeah. So these are gas molecules. This is gas. And this gas has a pressure of P1 and this has a volume V1. So this gas is exerting a pressure of P1 on the surface of the cylinder and on the piston as well. So on the lower surface of the piston and on the surface of the circumference of the cylinder and on the bottom of the cylinder. And the volume of this gas is V1. And also let's say that the temperature of this gas is T1. So I can clearly say this has P1, V1, T1 are the thermodynamic properties. If you recall chapter 3, what are thermodynamic properties? So I can say thermodynamic properties are characteristics which define a system. So this system has pressure P1, V1, T1. That's how I define this system here. Now this piston has a weight, W weight on it. Now this W weight is exerting a downward force, which is equal to W. Weight is simply mass into gravitational force. So we are exerting a downward force which is equals to W. Now what this W is doing, this W is not allowing the piston to move up because this gas has a tendency to expand. Okay, this gas has a tendency to expand. It is applying a pressure of P1 on the surface of the cylinder and on the surface of the piston. But since we have a weight W, on the top surface of the piston, this W weight is not allowing the piston to move up. So now why I draw this is to explain you quasi-static process. So through this diagram, we will try to see or try to understand what the quasi-static process is. So now in front of me, I have a PV diagram, a pressure and a volume diagram. And in the PV diagram, I have 2 points, 1 and 2. So this point has a pressure P1, volume V1, this is V1, this is P1, and this point 2 has a pressure P2 and volume V2. This has P2, V2. Also, these 2 points actually represents my initial state and final state. So state 1 is the initial state when I have weight W over the piston and it is stopping the gas to expand. So at that time, the volume of the gas is V1, pressure is P1. Now let's suppose I remove the weight W. So I remove it. So what will happen? Piston will move up because there is no force stopping it from moving up. So it will reach a point 2, which is its final state. And it will take a path to reach point 2. If you remember, we studied path, process, and cycle in last chapter 3. So this is the path it will take where its volume keeps on increasing and pressure keeps on decreasing till it reaches P2V2, which is the equilibrium state. Now, when I talk about quasi-static process, a quasi-static process is something. Can I say this is a quasi-static process? This is a process, right? Point 1 to 2 is a process. Why is it not a cycle? Because we didn't achieve initial state. If we go back to 1, 2, and then 1, then that's a cycle. But since we reach from point 1 to 2, that's a process. Now, can I say this is a quasi-static process? For that, we need to know what is a quasi-static process. So a quasi-static process means a process which is taking place in near to equilibrium states at all time. What does that mean? So I'm saying quasi-static process. So let's understand quasi-static process. So here quasi means almost. Quasi means almost. Static means in a state of rest, right? Not moving. That's static. So almost in a state of rest. Now this is important to note. We are saying almost in a state of rest, not in a state of rest. So a quasi-static process is defined in a thermodynamics as a process which is almost taking as such that each path along the process is at equilibrium state. Now, what is the path which we are taking from 1 to 2? We remove the weight W and boom, it go from point 1 to point 2, right? So in between, it goes from all these paths. But at all these paths, the system was never in equilibrium. There was a thermal, mechanical, chemical imbalance in the system. So it was never in a thermodynamic equilibrium. But what if I go from point 1 to this point. Let's say this is P1 dash and V1 dash, and then to this point P2 dash, V2 dash, and I slowly progress towards my final position, which is P2 V2. And all these intermediary steps, P1 dash, V1 dash, P2 dash, V2 dash, all these are equilibrium state, thermodynamic equilibrium state. So if that is the case, then my process will become a quasi-static process, which is almost in a state of rest, almost in a state of equilibrium. So for that, in picture, I'm only drawing 1, 2, 3, 4, 5, 6, 7 points, but in actual, this is infinitesimal points. There are infinite points because every process is not a quasi-static process. We are just assuming that each and every step or process we are going through or path we are taking has achieved thermodynamic equilibrium. So how do we do that? So when I divide the weight, this was the weight. So W is now divided among W1, W2, W3, W4 up till infinite. So infinite means many small weights. And now I have the gas here. Let me bring the green color back. So I have the gas here. Again, P1, V1, T1 is the initial condition. It is exerting these pressure, has a volume, and all these are exerting weights, a force, a downward force on the piston and letting them stop to move upward. Now, what if I remove W1, which is very infinitesimal small? So if I remove weight W1, let's say this was W1. So this is W1, W2, W3, and there will be many more. So if I remove weight W1, if I remove this piston will move up, right? It will move up and it will stop at one point because now it will move up till the force balances. So the pressure will increase or decrease. The pressure will decrease. So it will come from this point to this point, which was P1 dash, V1 dash, P1, V1, and it will stop. So this is an intermediary step here. Now I remove weight W2. So I remove W2 as well. It will go from this point to this point. I remove W3 as well. It go from this point to this point. Remove W4. And I keep on going till I remove all the weights and I reach the final state, which was point 2, P2, V2. So if you can observe, I have traveled the same process which we showed above, but this time, instead of removing all the weight at once, I gradually remove the weight by a very small amount so that the individual steps I go or I cross are at thermodynamic equilibrium. And now I can say this process, now I can say this process is in a thermodynamic equilibrium. Now 1 to 2 is in a thermodynamic equilibrium, also is in a quasi-static process category or is a quasi-static process. Now 1 to 2 is a quasi-static process because the path it took, all the path in between are at thermodynamic equilibrium with the surroundings. So that's what a quasi-static process is. Now, why do we read a quasi-static process. Why is it important for us to know what a quasi-static process is? Because when we talk about when we as we move ahead in our chapters, we will see we talk about reversible process, irreversible process. There are assumptions made, theorems which are derived. So quasi-static process is a process where quasi-static process is a process where I can go back to state 1 to 2 and then back to 1 to initial state. This is a reversible process. This is a reversible process. And how is that? Because now let's say I again keep on adding the weights. I keep on adding the weights. I add weight W2, I add W3, W4, and slowly I can go back from weight zero point 0.2 to zero point 0.1. Also, if I add all the weight at once, I can still achieve the same result. But will I know that it went through the same path? No. It might be a different path it took. Maybe it was like this, right? It could be a different path. Maybe it was like this. You never know. Well, it cannot be like this, but something like this. Could be any path. But if I want to know if is it the same path which I took, so that's a reversible process, which can take the same path which it took initially from reaching from one state to another state. That's a reversible process, and that's a quasi-static process. Now, another important thing in thermodynamics is a pure substance. So we are talking about pure substance. Why pure substance? What is the importance of pure substance? What is a pure substance? So a simple definition of pure substance is pure substance is defined as one which is homogeneous and is invariable in chemical composition throughout its mass. So this is important to note. Homogeneous, invariable in chemical composition. So homogeneous we know from our last lecture. Homogeneous means in chapter 3 we read homogeneous means which has the same composition throughout. And we are talking invariable in composition. So invariable in composition, we will try to understand what this really means. So these are all pure substance: air, steam, water mixture, fuel. Now it comes to my mind, how is air a pure substance? There are so many gases in air. How can we call it as a pure substance? So remember, a pure substance doesn't mean that it cannot contain a lot of different gases or different elements. It needs to be homogeneous. And what it means, homogeneous means it has one state. And invariable in chemical composition means, let's say air has 72% nitrogen, 20% oxygen, whatever, and other gases. So it should remain like that. So if I take air from California, and if I take air from Delhi, or if I take air from Berlin, or if I take air from Shanghai and do an analysis on it, I will find all the air of same mass has the same composition: 72% nitrogen, 20% oxygen, or whatever is the right number. But this is what the gist of the matter is. Similarly goes for steam water mixture and fuel. The composition should remain same. So that's what a pure substance is. Now we are talking about pure substance. Another important thing in pure substances, state of a pure substance. Now, in state of a pure substance, the state of a pure substance of a given mass can be fixed by specifying two properties, provided the system is in equilibrium. And this thing is known as two property rule. So we'll try to understand what this is. So when I say, hey, what's a state of a pure substance? So you just need two thermodynamic properties to define the state of a pure substance. It could be temperature, could be volume, or if it could be pressure, it could be volume, it could be pressure and temperature. Now, if you have a pure substance and you know the two thermodynamic properties, let's say I have air and I know, hey, this air is at temperature T1 and V1. I have thermodynamic relations which I can use to derive other values of that air. For example, I can know what's the relative humidity, I can know what's the pressure on that air, I can know other things, what it can do. So if you have a pure substance and you have two thermodynamic properties, I can find out other thermodynamic properties of that pure substance using thermodynamic relations which I have. So that's a two property rule. And this only applies for a pure substance. Remember, this only applies for a pure substance. So once any two properties of a pure substance are known, other properties can be determined from the available thermodynamic relations. So that's what the state of a pure substance. Something which I left for the last is how are these pure substance. So we know these are pure substance because these are homogeneous and have same chemical composition. Now, what are unpure substance? Did we give an example of an unpure substance? Example, unpure substance. If we're calling air and water mixture are pure, what is an unpure substance? So unpure substance, an example is air and liquid air. So if there is a mixture of air and liquid air, okay, this is not a pure substance because in air the composition of nitrogen, oxygen is different from what the composition of nitrogen oxygen is in the liquid air. This is the reason why this is not a pure substance. This is an impure substance. And again, you can see there are two phases. One is a gas phase, one is a liquid phase, which are existing together. So this is very important. These are very subtle things in thermodynamics, but these are very important things as we continue our process and we continue in our next lectures. If you like this lecture, please click on like button, share it among your colleagues, friends who may benefit from this lecture. Please click on subscribe and you can leave any recommendations, any questions you have in the comments or email, and we will see you in the next video. Thank you guys.